Okay, I think people are slowly coming in, but let's get started. So we have another talk from Yale University by Professor Jack Harris. So I think the cavity is just getting crazier, so buckle up. So yeah, Professor Harris, yeah, he's a professor at Yale University with a lot of recognitions and awards. To name a few, Vannevar Bush Fellow, APS Fellow, and Arthur Gil Memorial Prize. So yeah, recently he did this very interesting work of making a cavity out of helium. So let's hear about it. The floor is yours.
A microphone or yes? Yes. Okay,
you can do that.
Okay. Okay. Is this thing on? Good. That I don't know. Can folks on Zoom, can you hear me?
They're all muted now after the traumatic experience of the last session. Everyone's now muted.
Okay, so assuming that everyone can hear me, first of all, thank you so much to the organizers for organizing this, for the invitation to be here. And again, really like the idea of inviting physicists to a techniques-oriented workshop, like I feel like I've never been to one. So this is really cool and much appreciated because it does, our work hinges on learning a lot of these things from each other. So I'm going to tell you about an arguably crazy cavity that, and by and large, definitely a cavity. And also sort of the broader research program that it's part of, where I think you'll see some combinations of some very familiar stuff combined with less familiar things. But it's definitely cavities, it's definitely resonators. I want to start by thanking the grad students, postdocs, undergrad, and research scientists, in particular Yogesh Patel, who've led this effort. It's been a really long time trying to get this even to the stage that it is. Very much still a work in progress. So I want to thank sort of former group members. And then this isn't super standard, but I want to emphasize that our ability to do the things that we're doing absolutely builds on important results from the field by other folks. So I want to just give a nod to all the work that I'll be building on there. And of course, our funding agencies. So the outline, I'll begin by giving you one of the motivations for this project, which is to study macroscopic quantum phenomena. I'll describe why magnetic levitated superfluids are interesting for this, how we study some boring things like vibrations, some slightly more interesting things like optical cavities, and then why sometimes our cavities just explode. You may think this is an exaggeration, it's not. And I will tell you about some longer term goals. Okay, so look, the Royal Swedish Academy of Sciences kind of did my job for me, so takke veldig mye til alle dere. But this is, in any case, my own take on why you might be interested in macroscopic quantum phenomena. The first is just, it's amazing. Like, it's so cool that, for example, in Marcus Arndt's group in Vienna, they can take molecules that really look like this, launch them through meters of vacuum chamber, have them pass through real actual slits, real little holes, and then collect them one by one. These are these individual flashes here. And amidst the pattern of individual molecules, which really land with an impact like a particle, you see emerging from these flashes the pattern of the de Broglie wave interference pattern associated with the wave function of the center of mass of these objects. The fact that this works is just mind-blowing, even though it's textbook quantum mechanics. At the same time, sort of macroscopic has to do with the motion of relatively large things. The technology around acoustic devices is just insanely sophisticated these days, whether it's in your cell phone or at LIGO or doing all kinds of ultra precise measurements. And by and large, if you can take a mature technology and bring it into quantum regime, there are advantages to take. Lastly, there's the possibility that just, there really is something oxymoronic in this phrase, macroscopic quantum mechanics, and that there will be some fundamental surprise that is sort of outside the standard program. A particularly, fruitful conceptual thing to think about is that if you have a mass, an object that is like sufficiently massive that it deforms the geometry of space-time, that it produces a gravitational field, and it's in a superposition of locations. We have no idea how to describe this system at present. It's just simply an open question as to whether or not the geometry of space-time is in some kind of superposition, or maybe it doesn't do that, or who knows. Anyway, so lots of good reasons to think about exploring quantum mechanics on macroscopic scales. In this talk, I'm not going to get to any of this. None of this is going to take place in the experiments, but that's sort of the picture that we have in mind. The experiments that I'll be telling you about, this is really the picture. The idea is to have a sort of millimeter-sized drop of superfluid helium. I'll explain to you why millimeter is a very important size scale. Magnetically levitated in vacuum so that it is really very free of everything, to allow it to cool itself via evaporation, to send a laser beam in and excite one of its optical whispering gallery modes. And then maybe the idea is that the light that leaks out again will tell you something about the motion of this object. It's a cavity optomechanical experiment. So there are some reasons why this is particularly interesting. Just as an optical material, as a cavity material, liquid helium has zero absorption. And so in a room full of experimentalists, you should be very careful about saying anything is zero, but I will explain to you just what I mean by zero. Naturally a smooth surface, no kind of microfabrication. The hope is that there's some interesting quantum regimes in terms of optomechanics for having hopefully a very high finesse cavity in this very soft, cold object. I'll tell you about some longer term scientific goals around like testing aspects of the standard model of particle physics and looking at interesting aspects of superfluid helium. So this is maybe a little bit crazy. Like if you say, this is the cavity I want to build, this is not super trivial. On the other hand, the reason it's not crazy is because of the work of some of those people I mentioned before. The magnetic levitation of liquid helium drops has been done. People have shown that if little nano drops, at least of liquid helium in vacuum, are very good at cooling themselves off via evaporation. They really get very cold. And it's known that not liquid helium, but other kinds of liquid drops support extremely high finesse whispering gallery modes, and that you can even couple light into them from free space. No taper fiber or prism or anything like that. So our goal is to sort of combine all of these things at once. And the way that it works at this point is that you buy this very expensive thing from Oxford Instruments, and you wait a couple of years, and eventually it shows up. And really what it is just a basic cryostat with a magnet in it. The magnet, though, is unusual in that it's a 15 Tesla solenoid. That's not the unusual part. It also has a very large gradient in addition to just the overall field. And that's what's required for magnetic levitation, whether it's the frogs of Andre Geim or the graphite in your lab demonstrator or whatever. You need this combination of field and field gradient. What I'll be showing to you, all the data is taken by looking up a window at the bottom of this cryostat and looking up into the rather skinny bore of this big superconducting solenoid, looking up through a window into a cell that we put in there. The cell can be cooled down to about 1.5 Kelvin. When we want to make the drop, what we've learned to do is to put a little puddle of liquid helium on the bottom. And so, of course, above it is about an atmosphere of helium vapor. And then turn on the magnet. Sorry, this is where a lot of the money goes. But once the magnet is turned on, these green lines are the potential energy contours for a helium atom. Helium is not terribly magnetic, but of course it has a little bit of diamagnetism, just like a frog. And so if you design things carefully, you can have a minimum there. The thing that we do is up here at the top, we open a valve to a turbo pump. And basically the shock is enough that this vapor condenses a little bit, like a humid evening on a cold day where suddenly you get fog. The chamber fills with fog, the pump is running and is sort of evacuating all the vapor and pulling it out, but the little droplets are being held onto by the magnetic field, and it's some kind of fight as to who wins. So what I will show you now is a video of that process, looking up through the window into this cell, and it'll start just after the turbo pump has been turned on. The goal, of course, is to remove all of that uninteresting helium and end up with some sort of macroscopic drop there. So this is a video. It's playing now in real time, looking up this window. The pump has been opened up, and there's this swirling mist of liquid helium in here. You can see the drops zipping around as they're being pulled out. The pump is pulling things back into the screen. Gravity is pointing out of the screen at you. And what you can see is that the drops, in addition to getting pumped out, they do bump into each other. And as they bump into each other, they start to coalesce, until at the end of the day, there's a sort of millimeter-sized drop of liquid helium. This is levitating freely, not in very good vacuum at this point, and some substantial amount of helium gas in the background. But basically, this works, and you let the turbo pumps run and run and run and run, and the drop hangs out there, and that's how we end up like this. The longest we have kept a drop is 5 months. Yes, we named. So the drops, because it got to be so bad, being like, oh, well, remember the drop before, that really bad drop that had the blah blah blah, like, and now that they last for days and weeks and months, each one gets named after a bird, and we're going in alphabetical order. So this may have been Articuno. Legendary Pokemon, for those of you who don't have 14-year-old kids. And Kookaburra just perished, we're sad to say, after 5 months. No, let's talk, like, there are all kinds of interesting fates that they meet, but no, evaporation is not the issue, as I will show you in a minute. So there are a few things, once it's levitated, that we have to handle. The first is that just the center of mass. And unlike most sort of levitated optomechanics experiments, this is not the oscillator we want to work with. So mostly it's a nuisance, and we try to get rid of it. The drop is levitated. This is sort of a schematic. And so what we do is we send in a green laser beam, just bounces up and through the drop and comes back out on a photodiode. It's a very simple setup. And so you can imagine the drop looks like this with the beam going through it. And this is, if we shake the drop, in fact, you don't have to shake it. If we just watch its motion, you will definitely see 3 peaks in the spectrum at about 1.3 hertz and 1.5 hertz and 1.4 hertz. This is the X, Y, and Z normal motion of the drop. And this is very repeatable. You can tune it a little bit by varying the magnet currents, but basically this is sort of what it looks like. This is hertz. This is, again, room full of experimentalists. This is terrible, right? Because there's just a ton of vibration at a hertz. This is not good. Also, once it's in pretty good vacuum, there's no discernible damping. Like, I don't know what the Q is. It's not infinity, I'm sure, but like we can only put a lower bound on it. So mostly the center of mass motion is just a headache. So what we do is we use the brighter 1064 beam from our Mephisto or light laser, which is sort of 50 milliwatts instead of 50 microwatts. And the optical dipole force from this, we use to trap the beam and implement a feedback loop to suppress its motion. So if we do that, this is sort of the drop's motion record over a function of time. And if you first turn on the feedback and you get the sign wrong, it rings up some large amplitude, but then you switch the sign of the feedback and it rings back down. And the fact that there's a sort of 3-second ring down time here, when we know that without feedback, it doesn't ring down on the scale of day, means that if it's working well, it's suppressing the center of mass motion by a lot, at least enough for us to just move on and look at other things. So that's the center of mass motion. Where we do have some goals is looking at the normal modes of the surface, like at lowest order, just the prolate to oblate sloshing of the drop. And so to do that, it's the exact same setup, only we just modulate this 50 milliwatt control beam and sweep the frequency and record how much modulating this beam causes this beam to get modulated. The idea being that if this frequency hits a standing wave of the sphere, it'll ring up like that. And so this is a typical-ish measurement where we're sweeping the frequency of this drive over this range, and you see a resonance. And this is a fit to a single damped driven harmonic oscillator, just like you would expect. We know that this is the L = 6 surface mode, just from basic calculations. And so I guess I should say the surface waves are all spherical harmonics. That's just a standing wave on a sphere. And this is a picture of one of those, but there are, for L = 6, there are 2 L + 1 choices for M. And so in some ways, it's a little bit surprising that this fit really fits to a single resonance, because there are 13 normal modes here, right? They're all these normal modes, but apparently they're very nearly degenerate, which is just another way of saying apparently the drop is rather spherical. So we expect it, just based on what's going on in there, like the trapping fields, to have about a 10 part per million ellipticity, no more than that. And since this is not a terribly narrow line, we wouldn't expect to see these 13 different levels that are split by 10 parts per million. In some of our drops, I'll come back to this later, but at least in some of them, that's like the resonances really look this clean for lots of them. So in a given drop, you can measure the lowest resonance. This is really prolate to oblate. L equals 3, 4, 5, 6, 7, just all shown with their frequencies shifted up to L equals 12, up to L equals to 17. In some drops, we've measured up to L equals 100, but you can measure lots and lots of these. And again, in some drops, they all fit very nice to these single Lorentzians. And having measured them and fit them, you can extract their resonance frequencies and plot those as a function of the mode number. And this is the data. This is the sort of a fit. This is just the a priori prediction of elasticity theory, or linearized fluid mechanics. And the scary thing isn't that it fits the data, but that it fits it absurdly well. So this is 10 kilohertz modes when the residual is fraction of a hertz. And we've seen this again for up to 100 L's, which is about 1,000 modes in total. And the question I always like to ask is, well, is this weird? This just comes from F equals ma, which is true as far as we know. But it's a hopelessly simplified model. Like, we know that this is not just a homogeneous toy model. Like, this is a real object full of all kinds of weird stuff, and the fact that it agrees so well is surprising to me. At least it has a very nice practical consequence, which is that if we ever don't see this, we know there's something wrong with the drop, and that does happen sometimes. So that's the normal modes of vibration, at least their frequencies. One nice thing that we can do is, because we have all these nice measurements of the resonance frequency, and the fits to Lorentzians are so nice, we can just measure this curve over and over and over and over again. And in the time scale of hours, those frequencies all shift up a little bit. So what I'm showing you here is just taking that expression for frequency of a mode in terms of its radius and inverting it. So this is frequencies of a bunch of those different modes, each one converted to the inferred radius as a function of time. And the first thing you can see is that they agree quite well to within sort of a nanometer on this millimeter-ish sized object. And then the other thing you can see is that they are all agreed that the drop is shrinking. So the natural interpretation of this is definitely evaporation. So if you fit a straight line to this, this is evaporation at a rate of about 0.3 picometers per second of the radius shrinking. So this is century-ish lifetime in terms of just evaporation. That's not the issue. Good one. So the nice thing about liquid helium, in addition to like its purity and all this stuff, every single property is known, like not just the linear ones, the nonlinear ones, the dissipative stuff, the extreme out of equilibrium stuff. It's all really well known, often from like atomic level ab initio calculations. So if we know that the drop is losing this many atoms per second off of its surface, let's say, you know that its temperature is 270 millikelvin. It's just the latent heat of liquid helium and all this stuff. So that's the temperature of the drop.
List of the mode spectrum is just perfect, and now I see that it's systematically off.
Yeah, I said to 10 ppm.
But systematically.
Yeah, okay, so this expression is not exactly right. So why are all the L equals 5 frequencies a little bit lower than they would be given the frequency of the L equals 12 mode? Yeah, that's sort of what's going on at the 10 part per million level. Short answer is I don't know. There is a bunch of things going on, though. Like, our vacuum is very good. I'll tell you about that in a minute. But there's definitely some backstreaming from the room temperature part of the apparatus. And so probably some little amounts of nitrogen ice are building up inside the drop. This is going to change the mode spectrum. There are probably remnant vortex lines or rings inside there that can tweak the spectrum a little bit. Yeah, so the drop is definitely 270 millikelvin. Again, if you have a sort of square millimeter of liquid helium that's trying to evaporate and it can't get itself any colder than this, you know how much heat load is on it. It's 40 femtowatts of heat load is keeping this thing stuck in temperature. So at this point, you can ask, well, where is this heat load coming from? And the two most likely culprits are, well, we're shining 50 milliwatts of laser light on this thing. Like normally this would get pretty hot. We also know that our walls are at 2 Kelvin and you can't really pump all the helium gas out. So there'd be some heat load from that. As far as the optical absorption goes, again, if you have 40 femtowatts of heat and you're shining 40 milliwatts of laser light through the object, this is an absorption of no more than a part per trillion. So that's an upper limit, and given that it's sort of 0.5 millimeter thick, this would be the maximum absorption coefficient of liquid helium. If you say, well, how much helium gas do I need in my chamber, given that the walls are at 2 Kelvin, to put this heat load on the drop, that would be a pressure of about 5 × 10⁻⁻10 millibar. And from various cross-checks and the like, we know that it's this, or at least overwhelmingly that, which tells us more or less what our vacuum is, and it tells us that the absorption of liquid helium is still unmeasurably small, even at this level. So propagation lengths are more than 1 billion meters, which is good for making cavities. Okay, so a little bit more. I told you about the resonant frequencies of the normal modes, and this is, again, what it looks like. It fits very nicely, and it returns the drop radius to some high degree of accuracy. These are the line widths of each of those modes, and some of the scatter is scatter, and some of it isn't, which I'll be telling you about in a minute. There's also completely ab initio prediction for the damping rate of each of these modes. It's very well understood how a moving liquid surface gets damped by inelastically scattering the phonons that are bumping into it. This is basic hydrodynamics. And here's the no free parameters fit. Not fit, no free parameters prediction. And so if you build mechanical oscillators and your ab initio calculation is this good, you've hit it out of the park. Like this is amazingly accurate, but it's not perfect. So this is a theory developed by these two guys. I developed a theory, which is basically their theory times a fudge factor. And so taking their fudge factor as the fit parameter, it does a really good job. So loosely speaking, I would say that somehow, like, and I'll show you a lot more data in a minute, like this is capturing the right physics, but there's something that amounts to like an overall multiplicative factor that isn't included in their theory.
But it's also just a line, right?
What's the line?
Your fit is a line.
Well, the theory is a line. Ab initio hydrodynamics said that this should be linear now. I'm going to vary some more parameters in a minute. Okay, so here are some more of those parameters. The different colors are the L's, the different modes of the drop. This is the line width plotted here. And this is, we can control the drop's evaporation rate basically by spoiling the vacuum a little bit. And as I mentioned before, if you know the evaporation rate, I can tell you what the temperature is. So this is the drop temperature over not a huge range, but here it is. And this is the line width as a function of that for all those modes. These lines are that fudge theory. No free parameters except for an overall multiplicative factor, which is about 0.284. So this really indicates that that theory, the original theory, is getting the physics very much right, but there's just some sort of overall factor. This is for odd L's, all the L equals 3, 5, and 7 standing waves on the surface. Let me now show you the even L's, exact same data. Oh, sorry, before I do that, let me just, so where would a fudge factor come from? Here's my thinking, which is that the usual theory says you have this surface and it's getting bombarded by phonons from a thermal bath down below. And each phonon that hits the surface goes away and is never heard from again. It re-equilibrates. It assumes there's a large bath down there. In our experiment, phonons have a mean free path, which is much larger than the drop, 10, 20, 50 times the size of the drop. And so this is a different kind of bath. A phonon comes out of it, inelastically scatters, but then inelastically scatters again and again off of whatever this mode shape is. So I don't know enough about non-equilibrium statistical mechanics to say, but my hope is that someone thinks that this can result in an overall factor like this.
What's the time to transition?
Speed of sound is 238 meters per second, and this is a fraction of a millimeter, so it's about a microsecond to bang back and forth. These surface modes are kilohertz-ish. And okay, so that's for the odd L's. If I show you the exact same data for the even L's, here it is. The lines, again, are the predictions for just theory times this fudge factor. And for large L's, like up at, it's a little hard to see, but this dark green for 8, this brown for 10, is sort of starting to capture the data. But the lowest order modes, which in some ways like are the simple ones, just prolate to oblate, and then the next one, are way off in some sense. So there's also something that is differentiating the odd spherical harmonics from the even ones. And basically there's some physics that really impacts these even ones in a way that doesn't the odd. And again, we have a hypothesis here, though it's not quantitative yet, which is the following. Even modes are different than odds in the following way. Because of their shape, the phonons that are actually damping the surface, the normal incidence phonons that are really carrying away energy from the surface, bounce back and forth like this. And so when the drop is doing its prolate to oblate motion, it is taking those phonons and like stretching them like an accordion, and then compressing them and stretching them and compressing them. So it's doing some kind of work on this phonon gas. Whereas if you look at an odd mode, you can see that the place where the phonons are bouncing back and forth between, the ones that do most of the energy, are really just getting translated by the drop motion. So there's not this extra kind of Carnot cycle-ish expansion and compression of the phonon gas. So that's why we think these even ones are more damped than the odd ones. Okay, so that's the surface modes. So now I'll tell you about the optical modes of the drop. And basically, our hope was that we could just shine a laser beam past the edge of the drop, and that as it evaporates, it would occasionally become an integer multiple of the laser wavelength, and we would see a whispering gallery mode light up. And that is, in fact, what happens. This is the transmission through the drop. We're sort of dithering the drop and locking into it, so each of these is like the derivative of a resonance. But every 200 seconds or so, in this case, you see this repeating pattern of sharp features, which is to say one free spectral range of the cavity as it evaporates. So we can zoom in on those, and this is sort of what the peaks typically look like. And I have labeled these. I've said that this is TM and this is TE. These numbers are the radial mode number of the whispering gallery mode. And furthermore, actually know what the L is. The L for these is about 2,935. And I know that because we can compare it with exact calculations. So you may have learned at some point that if you have a dielectric sphere, you can solve Maxwell's equations exactly. No approximations of any kind. No paraxial, no quasi-normal mode if you don't want to. It's just spherical harmonics and spherical Bessel functions, match the boundary conditions, and that's it. And usually this is a starting point for your whispering gallery mode, your microsphere, because it's not really a sphere. It's not really a perfect dielectric, but this sort of gives you a nice starting point. Here we really have a perfect dielectric, no absorption, no inhomogeneity, and it's pretty close to a perfect sphere. So these modes, let me remind you, if you pick an L, which is effectively like the wavelength of the laser that you're sending in there, then you have a bunch of different mode indices. For a given L, you have the azimuthal mode index, which tells you sort of how equatorial is the mode you're talking about, and M will run from minus L to L. If I slice through the equatorial plane, you also have an integer that tells you how many nodal lines there are going out radially. And then you also have polarization. That's the sigma variable here. So you'll have a TE type and a TM type of mode, which look the same. So I haven't drawn them. For our drops, and so this is the theory that we use. For our drops, it's about 1 millimeter across. Our wave, we're using 780 nanometer light. And so that means L is about 3,000. There are about 3,000 wavelengths running around here. And because we're much better at looking at these kind of equatorial modes, we're looking at M's that are, let's say, plus 3,000 for the clockwise running mode. The radial mode number, in principle, can be any integer, but for all the data that I'm going to show you, it's sort of 1 or 2 or 3, because basically the index of refraction of liquid helium is almost that of vacuum. So it's not until the drop is even so total internal reflection is rather weak. It's hard to make the whispering gallery modes whisper. So if there's much sort of normal momentum to the wave, it's very good at leaking out again. So we can really only hope to see these few. But so anyway, that's what allows us to say that L is 2,935. That as far as we can tell at this point, it looks like the 2L+1 M modes are degenerate. Obviously, they're not perfectly degenerate, but within this line width, we don't see them. Again, we know that it's not just this L, but we know what the radial wave number is, and we know what the polarization is. And the polarization we also check just by rotating the input light and seeing if that makes sense. This is the sort of, the broad ones are the less skimming modes. The skinny ones are the more skimming modes. In principle, there'd be some even narrower, really, Q=1 modes, but we haven't seen those yet. The line here is just a phenomenological fit where each mode is treated as a Fano line shape, just to figure out sort of where the centers are and the like, and also what their line widths are. So this theory also gives you the leakage rate, so the finesses, and they agree for this Q=3, the whopping finesse of 14 is about what you'd expect just from Maxwell's equations. We can do this a little bit more systematically. So for drops of varying sizes, we measure the finesse as it shrinks, and indeed it agrees very well with just Maxwell's equations prediction. We can also look at the splitting of the polarization between TM and TE. It also agrees pretty well, but there's some funny stuff going on there. So long story short, we think we really understand what these optical modes are inside the drop, mostly. What I mean by mostly is if I look at sort of these narrower ones where like we don't want to make a 14 finesse cavity. This is a lot of effort to do that. So if we look at these sort of higher finesse ones, oh, there it is, and it fits nicely to a Fano, and the extracted finesse is about 500, whereas theory says it should be 3 times higher. So this is bad on 2 accounts. You want to agree with theory, and you want your finesse to be high. It's not happening. Same deal for the other one, and this is pretty common. So that's not so good. The other thing that's going on is, you notice when we sweep, there are these sort of funny features. And as I can't remember if it was Peter who said, like, this is a classic symptom of sweeping too fast through your resonance. And so this is a 1 second sweep, which didn't seem too fast, but we took the data again more carefully, and those ringing features are 100% repeatable. They are not an artifact of sweeping fast. They really are part of the spectrum. So I think we mostly know, again, what's going on there, but not entirely. So if the drop were a perfect sphere, and this were L=3000, say, there would be 6,001 perfectly degenerate modes that would be about, that narrow or whatever. We know that the drop has about a 10⁻⁵ ellipticity. And so that will take these 300, 400 terahertz modes and split them out over 4 gigahertz. So actually we expect the M's to get lifted out into a band that's about that wide. Definitely no resolvable individual peaks or anything, like the spacing between the 6,000 modes is much smaller than the line width. So sure, broadly speaking, you would expect to see a wide feature there, but why these funny oscillations? I think we know what's going on there, and it has to do with the subtlety of input mode matching between a Gaussian beam and a sort of high order spherical harmonic that lives in a whispering gallery mode. So things like this are somewhat known from the literature. Yeah.
When you say there's 6,000 modes, should I think of that as rotating about this axis?
Yeah, sure. They're the perfectly equatorial ones, and then there's the ones that sort of do this and this and this and the. Yep. And so, yeah, so definitely just our laser beam should not couple to the ones in polar orbit. So we wouldn't expect our laser beam to couple from M=3000 all the way down to 0, but some modest fraction of this band. And then there's some subtleties about why some of those members interfere with others to give you this funny pattern here. Yeah, so this is coupling in at least to the medium finesse modes. Yeah. We've never done that, but yeah, that would be a good thing to do for sure. But nevertheless, even as weird as this transmission looks, you can still lock the laser to it. So we lock the laser to that, and this is what we see. The transmission as a function of time is really quite stable, so it's happy to lock to this little floating drop of liquid helium. The lock voltage is running down like this, which is just the drop evaporating and the laser tracking it as it goes. So that's very easy to do that. Once it's locked, what we do is we monitor the transmission and take the power spectrum of it. And we're particularly interested in frequencies around the surface modes. So this is our effort to see the undriven motion of the drop surface waves. And indeed, you can see peaks at the frequencies you'd expect for the different surface waves. I wish that we had been able to do a sufficiently careful calibration to tell you what the area under these peaks is and whether or not this is just Brownian motion or not. We weren't able yet, but we hope to soon. But sort of rough ballpark, it's not inconsistent with just being the thermal Brownian motion. Okay, so some conclusions. Liquid helium is I wish I owned a helium mine because it is just an amazingly underappreciated material for quantum optics, quantum acoustics. It really does some incredible things. Magnetic levitation is not the solution to all of your problems, but it does allow you to levitate an object big enough to be its own cavity. And that's what we use. So these are some of the results I told you about: evaporative cooling, getting into ultra high vacuum, measuring the surface modes and whispering gallery modes. Still a certain amount of time? How much? Oh, great. Okay. So then I will admit, like as I tried to allude to, there's still some things that we don't understand. So it seems that some of the drops are spinning-ish. It seems that some of the drops explode as they cool down. And having said that, it's sort of hard to move on to anything else. So I will just tell you that when we first make the drop and you're pumping it out, there's sort of, you start in an atmosphere of helium, and after about, if it survives for 3 hours, it's going to make it all the way to ultra high vacuum. But in those intervening 3 hours, it's shrinking, it's sort of not cooling itself very efficiently yet, and sometimes it falls out, or sometimes it evaporates away to zero if the vacuum doesn't get good enough, fast enough. But we found that when we cool things down using a certain recipe, the drop would just disappear. And if you go back and look at the video, it looks like somebody hit it with a tennis racket or like somebody burst a water balloon. It's very fast. So eventually we got high-speed video of this, and that's what I'll show you now. So this is sped up by a factor of 16. This is the dropped one. Oh, let me go back. So there's suddenly like this little ping and a ripple started to move through the drop. That's the start of this weird event. So this is slowed down by a factor of 16. Ping, little ripples. That can't be too much of a problem. And oh, okay, so the video is a little bit shorter. Is it going to run again? But yeah, you're looking up. This is the drop flying apart, and in the rest of the video, you can see like all the parts of it flying around and banging into the window and bouncing off again. Like it literally self-destructs, flies apart. So again, like actually almost everything that I've told you, we have a hypothesis, but nothing quantitative yet. So what we think is going on is the following. When the drop is first made and it's a normal fluid, you saw it's a very messy process. It could well have some net rotation. Okay. Then you start to pump it. It's a normal fluid. It's happy to rotate like a rigid body. Then when you start to pump it out, it is getting colder and colder. And at some point, part of it becomes a superfluid. And the superfluid cannot rotate that way. I'll say more about that in a minute, but it's sort of, if it's going to contain any angular momentum, it's a little bit weird how it does so. So it becomes a bit, we think, like the ice skater pulling in their arms and spinning faster and faster, because the amount of normal fluid, which starts out as like a milligram, let's say, is becoming more and more superfluid and less normal fluid, but it has to maintain its angular momentum. So that normal part is probably spinning around faster and faster, and there's a point where it is spinning faster than the speed of propagation of a surface wave. And at that point, that's effectively a shock wave. And that's what we think launches the surface. But if you notice, anyway, we just rebuilt this cryostat to have side view mirrors, so we can actually get a 3D picture of what's going on and hope to understand that better. So that's the exploding cavities. If anybody else has exploding cavities that they're going to talk about, that would be cool. So let me know. Yeah. It seems to initiate from somewhere. So yeah, if you watch the video, there's like a definite moment bang where it starts. And I think that matches the speed of propagation of a surface wave, not of a sound wave. So I think that's something happening on the surface. But beyond that, I can't really tell you. Or let me say it another way. If one of the surface modes is going to become unstable and just sort of ring up, essentially, maybe it is, in fact, this surface mode, the one, sort of wavelength is this big on the screen. Maybe it's starting to ring up until finally flies apart. Yeah. Okay. How many minutes now?
Including Q&A, you have about 7.
Okay, so let me tell you one last thing, which is when we measured the normal modes, I made this surface modes. I made this point like, oh, it fits beautifully to a single harmonic oscillator. This is true in a minority of the drops. In most of them, we see things like this, where this would have been just a single peak. And in fact, so instead there are 3 peaks for this L=3 mode. And this puzzled us for the first time because the first bunch of drops we made only had a single peak. And while we were trying to figure out what was going on, we were just remeasuring, and a week later, it went back to this perfect, apparently degenerate peak. And then we thought, well, it must have been fooling ourselves, so we're trying to figure out what was wrong with the data acquisition and stuff. And a week later, it looks like this. And we went back in the cryostat log to figure out what was going on. And basically, between each of these events, there's what we call a puff, which is a sort of seconds-long worsening of the vacuum, not by very much, but a little bit. And this is not sort of unique to the L=3 mode. When it's doing this multimoded behavior, all of the modes look not like single Lorentzians. They become split into some kind of multiplet structure. And if this was an atom, you would say, well, you didn't zero out the magnetic field, right? But it's not a magnetic thing. But we suspect somehow this is basically rotation. This is the equivalent. So why would a puff of gas give the drop some rotation? Well, if this is the drop and some helium atom slams into it, it adds angular momentum, just P cross R. And if this were a drop of water and it got slammed into, it would eventually rotate like a rigid body. But liquid helium at this temperature has no normal component. And the only way that the superfluid can rotate is by forming a vortex line. Which is qualitatively like rotating, but it has a different flow field. It's divergent at the center. So if this is what's going on, then does that explain the funny behavior of the surface modes? The answer is that order of magnitude, it's correct. So the speed of so you can think about like, look, I have the surface mode. It's a standing wave. It's running waves going like this and making a standing wave. But if the fluid is itself rotating, one of these will travel faster, and you'll get to sort of, you'll get a frequency splitting between these two. So if you have one vortex line in liquid helium and the drop size is 0.1 millimeters, the speed of rotation out at the surface is about 1 millimeter per second. The surface wave propagation is about 1 meter per second. So you'd expect to see modes lift their degeneracy at sort of the part per thousand level, which is about what we see, fraction of a hertz on hundreds of hertz. You can do the actual calculation, though, and in a rigid liquid, the surface modes split just like Zeeman. In a vortex flow pattern, though, there's this very funny thing, which is that all the positive M modes go to one place, all the negative M modes go to another place. It's just sort of how it works out. And if you look at our data, it's not really doing either of those. It's neither sort of spanning out nicely or just splitting into 2 peaks. And so our hypothesis is that what we have is a vortex line because the center order of magnitude seems right, but since it's not making this nice pattern, it's probably not running dead through the center of the drop, in which case we'd be doing this, but taking on one of these shapes here. And these are, in fact, the known equilibrium configurations of a vortex line and a drop. And we just don't know yet. We don't have a calculation that would tell us, okay, what would the fingerprint of such a line be on the surface modes? But again, hopefully we'll have that someday. Okay, so that's really it. Oh, long-term goals. There's some fun things to do here. But I think in just the interest of time, let me thank again the folks who did the work and our alums and the people whose work we've built on and our funding agencies. And thank you for listening.
Okay, thanks, Jack. Oh, a question. Okay.
Thank you. It's very interesting. So my question may be kind of naive. So when you create this helium droplet, is always kind of created the same location or same position?
Yeah, pretty much. That's defined by the
Okay.
Magnetic fields. Yeah.
Okay, got it. So and also for these resonances, actually kind of in a few hundred hertz. So pretty much kind of imposed by this magnetic field resonance.
No, not at all by so the magnetic field tells you that the center of mass motion is going to be 1 hertz. The surface waves, this is set by the surface tension of the liquid helium, and the magnetic fields have almost no impact on that.
Okay.
It's just like if you have a cup of water and you tap on the side, you'll see certain standing waves in there. That's what we're looking at.
But you're sweeping a laser, right? Sweeping a laser wavelength, right?
Laser. When?
So when you have this like control and also this like red and blue laser to excite your Wismager modes.
Yeah, sometimes we sweep the laser.
Okay, but how do you actually get this like a few hundred hertz?
Oh, there we're just amplitude modulating the laser. We
Okay,
just
got it.
oscillate the intensity and see if that makes the drop.
Okay, cool. Thank you.
Too many questions. You first. Is there any possibility to actually trap some small bubble?
Yeah. So liquid helium is very good at not having any impurities unless you put them in. And the most famous impurity maybe is the electron bubble. So a single electron forced into the bulk of liquid helium makes a 2 nanometer bubble that co-moves with the electron. I guess in principle, you could make such a thing. It would be a little bit complicated in the large magnetic field. We haven't done this. There's a whole sort of cottage industry, though, of physical chemists who dope nano droplets of superfluid helium with interesting molecules, and then use that helium drop with 1 molecule inside of it as kind of a little cryostat, and then they do spectroscopy on the molecule. Basically, the helium drop makes it very cold, but because it's a superfluid, it doesn't sort of mess with the molecule very much.
Really cool stuff. So I have 2 quick questions. One, there were 2 different events, and the spectra look different in the 2 events. Should I understand it's sort of the orientation of the angular momentum kick is presumably different, and that's what causes.
So I think if you have a sphere of liquid helium and a hot helium atom goes racing through it, it leaves behind a train of vortex rings. And depending on what happens next, the vortex rings may bump into each other and annihilate. They may shrink to nothing. But depending on sort of how they swim around, they can either end up in sort of a stable motion within the drop, or they can bump into the surface and form a kind of trapped vortex arc. And so, and the precise configuration that you get, I think, will make the surface modes have a different signature.
Cool. And the second question is, could you imagine that you inject another laser beam and essentially use it as a stirring beam to actually ride in a vortex?
Like we're literally setting that up right now.
Yeah, that'd be super cool. The idea that you sort of ride in deterministically.
Our colleague Charles Brown loaned us a 200-watt laser, and we've installed the servo.
So maybe along those same lines, some of the original vortices that, for instance, I think Eric wrote in Cornell, he did it via phase imprinting. So could you imagine that instead of stirring, in some sense, you basically phase imprint?
I think you need access to the actual atomic transition, don't you?
Yeah, that's a good question. No, I think this is a ground state wave function. Maybe people who do this stuff can, weigh in better than me.
Yeah,
really need a Raman transition.
But it's 20 electron volts. So you'd be, it's this versus that.
Okay.
Can you trap and produce several of those?
Every once in a while there's vapor, sometimes we get 2 big drops, and while there's vapor, it sort of forms a cushion between them and they don't coalesce for a while. But eventually they do. Because there's only one.
But you could measure what's happening while coalescing in print. Not tomorrow, but.
Yeah. The trap really only has 1 minimum. So it's a little bit hard to get to in there. Sometimes, we don't know how much stray charge the drop has. If you really charge them up, maybe you could keep them apart a bit.
I was also curious about the loading process. Is this a process with the mist method that you knew before you'd bought the cryostat, or some from other
No,
previous
the
groups?
one group that had done levitated drops before, which is the Maris group at Brown, they just had a capillary line that was positioned rather close to the trap center, and they would feed liquid in until a pendant drop grew and eventually broke off. And that's what we thought we were going to do, but this just seemed to work a little bit better.
Cool.
Okay. Oh, there's one more question.
All right, so here's a dumb question.
Okay.
So can you sense any change to the droplet from cosmic rays going through it?
We do see funny little events in the drop. So we can measure that frequency to part per million or something like that. And that's what, over the course of hours, you see it drifting. But as we learn to do this measurement better, like we can take such a measurement every second, and the error bars are tiny. And there are occasionally little weird events. And I have mostly thought, well, this is like a vortex, two vortex lines finally find each other and reconnect. But yeah, it could be an electron hopping on or off the surface. It could be a cosmic ray. We just don't know.
Okay, great. I think that was a lot of questions. So let's thank Jack again.
Thank you.